We're now ready to look at the first derivative test. So, in a previous section, what we learned was that a function, if it had a relative min or a max, then that relative min or max is going to occur at a critical point. Okay? Now, we're not guaranteed that every critical point will be a relative min or max, but if there is a relative min or max, we do know that has to occur at a critical point. And so the first derivative test is a way of testing that critical point to see if it's going to be a relative min or a relative max or neither of them. Okay, so this is kind of the tool that we need to analyze each critical point of a function. So what we're going to say here is let x equal c be a critical point of a continuous function. Okay, and so we're going to say f of x is differentiable over some interval containing c, except possibly at c itself, because remember a critical point could be when the function's undefined, either when the derivative is 0 or the function's undefined. Okay, so what the first derivative test says, then, as you move across an interval, so let me draw a picture here. This says if the derivative changes from negative to positive, then x equals c is a local min. So let me show you what this means. So there's c, and so if the derivative is negative, what we've just learned is the function is decreasing, and then if the derivative is positive, it's increasing. So this means this must be like this. So this is f prime of x is less than 0 to f prime of x is greater than 0. And then here, this is where it's equal to 0. Right? F prime of x is equal to 0. So this is the critical point where you got the horizontal tangent line. And here, the function is decreasing. Okay? It hits that minimum, and then it's increasing. So what it says is if the function, or if the derivative goes from negative to positive, or if it goes, if the derivative goes from negative to positive, then you're going to have a local minimum. Well, the next thing just says the opposite here. If it goes from positive to negative, if the derivative goes from positive to negative, then it's going to be a maximum. And so this means if it goes from positive, it means the function is increasing on this side until it reaches this maximum point, and then it starts decreasing, right? So this would be where the derivative is greater than 0 here, and the derivative is less than 0 over here, and then here at this point, you got the horizontal tangent line where the derivative at c is equal to 0. This should be a c here. So if on the left side of c, the derivative is positive, so that it's increasing, and then it changes to be negative, then what you got is a maximum. Okay, so you got a minimum. If it goes from negative to positive, it's a minimum. If it goes from positive to negative, it's a maximum. And then the third thing says if it does not change signs at x equals c, then it's neither a min or a max. So this is basically, oops, I shouldn't have drawn that, but this is basically a place like if this is c, it'll be something like that, or possibly if this is c, it could be something like this. So here you got your horizontal tangent, but here it's negative, the derivative, it's decreasing, it flattens out, and it decreases. So here you got like f prime of x is negative, less than 0, and on this side f prime of x is less than 0. So it's just decreasing the whole time. It does flatten out, and then here at c it is equal to 0, so it flattens out, but it doesn't turn around. Okay, the derivative doesn't go from negative to positive. It goes from negative, flattens out to 0, and then goes back down. Okay? And then same here, where, okay, it is negative here. I'm sorry, it is, at C, it is 0, but on this side, f prime of x is greater than 0, and here it's still greater than 0. Okay, so it's increasing, it does flatten out, but then it just goes and increases again. So in other words, if the sign does not change at C, as you go from one side of C to the other, then it's neither a min or a max. Okay, so if it goes from negative to positive, it's a min. If it goes from positive to negative, it's a max. And then if it doesn't change, then it's neither. Okay, so that's the first derivative test. So what I said in the last video is we're going to illustrate this here with this is the example that we were doing. Okay, so we wanted to find when this function was increasing and decreasing, and what I did is I found the critical points, and these are the critical points. This is when the derivative is equal to 0. Okay, and so then we could make this table. And I want to show you something else about this too. This is like negative infinity to negative 2, negative 2 to 2, 2 to infinity. And this would be x equals negative 2, negative 2. This is x is equal to positive 2. So these are the two critical points dividing your domain up into 3 spaces. And then we saw that this here was positive, this one was negative, and this one was positive. Okay, and what I did is I picked a test point in each of those intervals. Let me tell you, I probably would not, if I were to do these on my own, I probably wouldn't have picked a test point. Okay, what I would have thought in my mind is that this here, I would have looked at the graph of the derivative, and I would have saw that this was a parabola that had a 0 at negative 2, and it had a 0 at 2, and it was a face-up parabola because the leading coefficient was positive. And so I knew that this would be the derivative, f prime of x would be this. And so clearly it's positive here, right? And clearly it's negative here, and over here it's positive. So just by telling if the derivative is above the axis, I could even graph the derivative. I'd find the zeros. Wherever it's above the axis, it's positive. Wherever it's below the axis, it's negative, and so on. So that's another way you can find this. Okay, but what the first derivative test says is this. It says that at this critical point, it is going from positive, so it's going from increasing to decreasing, right? So this critical point is a max, and then over at this critical point, it goes from decreasing to increasing. So this critical point is a min. And so remember this is the derivative here. So if I graph the original function, which I did here, so this is the original function, and you can see indeed there at negative 2 it is a max, at positive 2 it is a min. Okay, and so that's how that first derivative test works. Kind of handy there. So let me do, I have one more to do here. Let's try this one. Sorry for the mess there. So let's try to use the first derivative test to see where this function might have min and maxes. So I'm going to take the derivative. I'm going to get 4x cubed minus 9x squared oops, I'm sorry, I think this should have been a 2. I'm pretty sure that should have been a 2. So that this would be 6x squared, and then maybe not. Maybe that should have been a 3. This one might not be what I want it, might not do what I want it to do. I wasn't thinking. So let me just check and see here. So then this would be plus 18x. So I get this, and then I could pull out, okay, this isn't going to do, I don't think, what I want it to do. I could pull out an x here, and I would get 4x squared minus 6 x, and then this would be plus 18. I don't think that's going to do what I want it to do. I can pull out a 4. Well, let's see what if it's going to do what I want it to do. I was picking this to do something special. If I pull out a 2, I get this, and I do get this would be plus 9. It's not going to do what I want it to do. What did... Oh, and I deleted the function in there, didn't I? Oh, I am so sorry. Let me look and see what I had on my sheet of paper. Sorry about this. So let's do... So I'm going to cross this out. And let me try this one. So I made a mistake. I know what I did here. So this is what I had to begin with. So, okay. So this will work. I think this will work. No, it does not work, does it? But if I put a 1/3 here, it'll work. Okay. Okay, so let's try this. Sorry about that. Okay, so now I want to find where the min and I'm going to use the first derivative test to find where the min and the max are of this cubic here. So I'm going to take this derivative, and I'm going to take the derivative, so I lower the 3 and subtract 1, and I just get x squared. This is minus 6x, and then this would be plus 9. And then I'm going to set this equal to 0. And we see that this thing factors. This is what I wanted it to do. I wanted it to be a binomial squared. And for some reason I thought my function that I had created was a binomial squared. This is what I wanted it to do. And so then I only have one critical point here, and it is at x equals 3. So this is my critical point. So this is going to split my domain into negative infinity to 3 and 3 to infinity. Okay? And then I can pick a test point here, or I can look at this derivative here, this parabola. And if I look at that, then this thing, which is really y equals x minus 3 squared, okay, it's really that. And so this is really a parabola shifted over 3, and it goes down, touches, and then goes back up. And the whole point here is that here the derivative, so this is x equals 3 is the critical point. Here f prime of x is greater than 0, and here f prime of x is greater than 0. And so it ends up being neither a min or a max. It's positive, and then it stays positive. Okay, so it's, and let's actually graph this so we can see what it looks like. So 1/3 x cubed minus 3x squared plus 9x. So if I graph this, we'll do it in a standard window. There it comes. And what you see here, and I guess I could probably change my window a little bit. Maybe change this from -5 to 15. And so you see the function actually going up, and it's flattening out at 3, and then it goes back up. So here the derivative is positive, and it flattens out. It goes to 0, but then it doesn't turn around and become negative. What it does is it just goes back up. And so this is a critical point, but it is neither a min or a max. And that's what I was wanting to show, an example where it is neither a min or a max. So here, this is the original function. It's like going up, flattening out there, and then going on. So this would be y equals f prime of x, and this would be y equals f of x. So that is the first derivative test. You're basically finding the critical points. You can set up a table, and then in each interval you find whether the function is increasing or decreasing. And then, depending on the signs here, if it goes from positive to negative, then that critical point is a local max. If it goes from negative to positive, it's a local min. And if the sign does not change, then it's neither one.